Game devs, do you know what game I think is the most overdone for tutorials on YouTube? Flappy Bird. So, do you know what I think is the best game for you to clone to learn game dev? Now before you click off the video, hear me out. I challenged myself to create this Flappy Bird style game in Godot 4.3, but I put my own spin on it. I wanted to do it using only one script and keeping it under 100 lines of code, but still add the expected features like a start screen, music and sound effects, parallax background, animations, spawning in obstacles, score system, increasing difficulty, and a game over screen, and add some features of my own like pickups and power-ups. That's right, all that in just one script. No complex setups, no huge code base. But can it really be done? Stick around as I walk you through my approach, share some of the challenges I faced, and show you the final results. And find out why this is a good place for beginners to start. I've also linked all the free assets I used in the description and added timestamps, so feel free to flap your way around the video if you like. But first, I'll answer some questions you may be asking yourself. This makes it easier for beginners to think about and understand the code by keeping all the logic in one place. This makes errors easier to find and fix bugs. It also reinforces understanding the fundamentals of basic concepts without complexity. In Flappy Bird, we'll discuss core concepts: collision detection, input handling, object spawning, and scoring. And because of its quick feedback loop, it will be easy to playtest and refine. This will encourage concise, efficient coding. It really demonstrates how much can be accomplished with minimal code. It also encourages you to think logically and, in my opinion, improve your coding skills. For those of you out there that don't know what Flappy Bird is, it's a game where you play as a bird that needs to flap its way through scrolling pipes that protrude from the top and bottom of the screen. If the bird hits a pipe, it's game over, and you get points for every pair of pipes you pass. I've decided to discuss the various aspects of the scene tree, the systems used, and the code as they appear in the game. That way, I think it would be easier to follow along because we'll be discussing things as they happen in the game in real time. We may have to skip ahead and come back to some systems later on as needed, to keep the focus on one specific idea at a time. But enough explanation, let's fly in. Let's first take a look at the scene tree. I use these empty nodes to hold multiple nodes of similar types together, like the node 2Ds I use for the background, the ceiling, and the ground, and similarly for the audio players for the music and sound effects. Looking at this tree, we can see that there are quite a number of different node types being used. But by doing it this way means that we can group nodes together to keep things organized. We'll be looking at nodes like Node 2D, Parallax 2D, Sprite 2D, Audio Player nodes, Canvas Layer nodes, Label node, Texture Rect node, Animation Player nodes, and the Timer node. We'll also be looking at systems like scripts, signals, showing and hiding nodes, and groups when we discuss spawning and obstacles. This is more of a discussion than a tutorial, so I'm assuming that you already know the basics of the Godot user interface. That being said, it will still be easy to follow along and understand the concepts being used. First, I use a canvas layer node to hold all the UI. Note there are multiple ways to do anything in Godot, and the good thing is that Godot tells you all the ways that you can do this. For example, you can add nodes to the tree by clicking on the plus button or by right-clicking and choosing Add Child Node. Now, a really cool thing about Godot is that if you hover over the names of things in the inspector, Godot gives you a little description of what they are or what they do. So I encourage you to give this a try. I use the canvas layer to hold all the UI. All the nodes have cool icons that distinguish them from one another, so they are easy to recognize in the tree. For the score, I use a label node, which is a control node used to display text. For the game over and get ready screens, I use a texture rect node, which is a control node that displays a texture. To display the texture, all you have to do is drag the sprite in the file system to this texture field in the inspector. I use a node 2D as a parent to hold all the textures for the Flappy Flight title. You can toggle the visibility of nodes on and off by clicking the eye icon on the right of each node. To start the game, I used a button node, which is a themed button that can contain a text and an icon. I will use this to trigger the start event, but more on that later. I have created references to various nodes that I'll be using in the script, so look out for these. During the video, if I refer to plane in the script, for example, just consider that I'm referring to the area 2D of the plane in the scene tree. If I refer to game over in the script, I'm referring to the texture rect node called game over in the script, and so on. The ready function is executed when the game starts and sets things up. So in this case, I decided to hide the game over screen by calling the hide function, show the get ready screen, and pause the game by using the get tree function and setting the pause value equal to true so that the game starts in a pause state. By default, Godot's built-in functions will be dark blue, and I will be using a lot of them, so look out for them as we go along. The get tree function is a really commonly used function. All it does is returns or gets the scene tree that contains the node. On a side note, you are able to get to the documentation really easily in Godot. There are 3 buttons that help you with this. The Online Docs button that will open the online documentation, the Search Help that searches the reference to a specific term used in your code, or the Doc button in the inspector, which opens the documentation for the selected object in the inspector. We will use the Start button to emit an unpressed signal that will call the functions that we need to get things going in the game. First, we unpause the game, then we start spawning in hills, which we will look at later, and we hide the get ready screen. Now you may be wondering, if the game is paused, how we are able to click the pause button and trigger the event. And that is a really good question. This is possible by going to the node class in the inspector and changing its process mode from inherit to when paused. Now that the game has started, let's take a closer look at our player character. An Area 2D is lightweight and sufficient for detecting collisions needed in this game. It simplifies movement logic since gravity and input forces are manually applied, and also avoids any unnecessary physics engine calls for this simple game. I also use an animation player to add a slight rotation to the plane when the fly input is pressed, instead of coding in the rotation. The reset function that will just cancel out of the animation if the animation is currently playing when the button is pressed, and an animated sprite 2D to handle the fly animation for the plane, and lastly a collision shape 2D to detect the collisions. In the script, I set up a few variables for the plane: gravity, which will make the plane fall, upward force, which will make the plane fly, and a plane velocity, which will be the current velocity of the plane, and set that equal to 0. I also made a boolean variable for the game state, is game over, and set it to false by default. Now, what's the physics delta function, and why do we use it here? The physics process delta runs based on physics ticks per second, which is typically set to 60 times per second. This is perfect for things that need smooth, continuous updates, like gravity pulling the plane down and the position changing. The gravity application simulates the force that pulls the plane downward, just like how it works in real life. Without this, the plane wouldn't fall. Position updates takes care of moving the plane up and down, and it adjusts the plane's vertical position based on the gravity pulling it down and the upward force from the input. In Godot, the process delta function runs every frame, where delta is the time between each frame, and could be used for input. But I chose to use another really cool function to handle the input in this game. The function input event is a built-in function in Godot. It's part of Godot's input processing system and is called automatically whenever an input event occurs, such as a key press, a mouse click, or a touch event. So this name cannot be changed if you want Godot to recognize and call its functions automatically. It's part of Godot's predefined function names, also called callback functions, that all follow specific naming convention. This approach is arguably better than checking for input in the process function, which happens every frame, which will also work, but I'm not going into detail on that at this time. The game listens for a specific action from the player. In this case, UI accept is typically linked to pressing the space key or tapping the screen. It's like asking, did the player tap the screen or press the space key? If the answer is yes and the game isn't over, the code sets the plane's velocity to an upward force. This gives the plane a little boost to move up, kinda like flapping the wings, but for a plane. Then it plays the animation to tilt the plane upward, providing visual feedback that matches the movement, making the game feel smooth and responsive. What happens if the player spams the fly input? Well, this is where calling the reset function before playing the animation is helpful. It will simply reset the animation before it's played, giving the impression that the plane is rapidly moving upward. To add more of a challenge to the game, we can set the is game over to true if the player gets to the top of the screen or at a certain point at the bottom of the screen. And as we will see later, if the player crashes into the obstacles. We can do this by calling the endgame function. Here we can stop spawning in obstacles, show the game over screen, make sure that the get ready screen is hidden, and play an explosion sound. We will look at playing sound a little bit later on in the video. And if is game over is true, we also want to return out of the physics process function to stop any further physics processes. I will use a timer node here, set the wait time to 1 second, and spawn in obstacles when the timer reaches 0. And will control the difficulty by changing the speed at which the obstacles move towards the player and the wait time of the timer. For now, let's take a look at the obstacles. I basically used a Node 2D as the root node and used Area 2D nodes with collision shapes and sprites for the obstacles. And as a bonus, I added an extra Area 2D node with a collision shape and a sprite for a medal to add extra points. This little box here means that it belongs to a group, which I will use to instantiate it into the scene. I made a couple variations of this, one with the medal to the top, another with the medal to the bottom, and one with no medal. To instantiate them, I made an array of preloads. Next, we create a variable called random index. The rand_i function generates a random integer, and the %hilltemplates.size path ensures that this integer is within the range of available templates. By using the modulo operator with hilltemplates.size, we ensure that this random integer is within the range of available templates. This means that the random index would be a valid index for the hill templates array. We then create a variable hillPair using the random index. We select a template from hill templates and create an instance of it with the instantiate method. This means we are creating a new pair of hills based on a randomly chosen template. We then set the position of this new hill pair. This path sets the horizontal position to 1000, placing it off screen to the right. The vertical position is set using rand_f_range -150 and 150, which generates a random floating point between the numbers -150 and 150. This random vertical position adds variety to the game, making it less predictable. Finally, we add the newly created hill pair to the scene tree as a child node. This means that it will now be part of the game, rendered on screen, and will interact with other game elements. Now that we have the hill templates in the scene, it's just a matter of moving it towards the player. For this, let's set up a few variables. The hill speed is the speed at which the hill moves. The hill speed time change is the amount of time that will be used to change the wait time of the timer to increase the difficulty. The hill spawn time is the time that we will set the wait time of the timer to be when the game starts. The hill spawn time change is the time that we will decrease the spawner wait time by to increase the difficulty. And the min spawn time is the minimum time that the wait timer can be set to. In the process function, I will use a for loop to get all the hills in the tree that is in the group hills that we set earlier. Inside the loop, this line here moves each hill to the left. The hill speed determines how fast it moves, and delta ensures that the movement is smooth and frame rate independent. This means that regardless of how fast or slow the game is running, the hills will move consistently. If the hill position X is less than -100, it is off screen to the left. Then hill.queueFree is called to remove it from the scene. The queueFree function schedules the node to be safely deleted at the end of the current frame, preventing potential issues that can arise from immediate deletion during the loop. Increasing the difficulty is really easy. I first check if the score is a multiple of 20. So if the score modulo 20 equals 0, that means the score is exactly divisible by 20, like 20, 40, 60, and so on. When this is true, it's time to increase the difficulty. Let's first decrease the spawner's wait time. This line shortens the time between the new obstacles. We subtract a little value called hill spawn time change from the spawner.wait time, making the hills appear more frequently. But we don't want the value to drop below the min spawn time. So we use the max function, which returns the max value, in this case the min spawn time. Finally, we speed up the hills. This increases how fast the hill moves across the screen by adding a little more speed to the hill speed. We're using a match statement here, which works like a series of if-else conditions. It checks the name of the area that the plane entered and decides what to do based on the name. If the area's name is hill template, it means that the hill hit one of the obstacles, so we call the endgame function, which we previously discussed. If the area's name is score trigger, it means that the plane successfully passed an obstacle without crashing. I had set up these variables to handle the scoring: a score variable, a score to add variable, and an extra score variable. First, the add score FX gets called to play the sound effect, update the score label text, and call the increase difficulty function. Then score is increased by score to add. If the plane collides with the area named extra points, then add score FX is called. The extra score is added to the score, and queueFree is called on the area to remove it from the scene. To handle the sound, I added audio stream player nodes for each sound and dragged the sound file into the stream field in the inspector. For the level music, I simply checked the autoplay box so that the level music would play when the game starts. Then I just called the .play function at the various points in the script where the sound is needed to be played. Luckily for the scrolling background, actually no code is needed with the new Parallax 2D node. I used a Node 2D to hold the Parallax 2D node and a Sprite 2D node as a child of it. Then in the inspector, I set the repeat size to be the horizontal size of the background image and the auto scroll to -5 pixels to move it to the left, and the repeat times to 1. I had a similar setup for the mountains at the ground and also the ceiling, so it looks like the plane is flying through a cave. But I changed the scroll speed to -10 to give the illusion that they were closer to the player. And that's it, the game is complete. Did I manage to do it in less than 100 lines of code? Well, I say I came pretty close because I got to 108 lines, which is including white spaces and comments. So that was not too bad. Now, this is a really cool first start in my opinion. It really forced me to think about the way the code was written and structured, and the pickup was a really cool twist to the game. I was also thinking of adding a feature where if the player picked up a gas tank, the player would have two-way control of the plane for a short time, and then the controls would revert to the Flappy Bird style control. Okay, so we're at 108 lines. Let's see how we can do this efficiently with as few lines as possible. To get the fuel system working, we need a fuel pickup that gives the plane a temporary boost of fuel. When the player gets it, it will activate a timer that lets the player control the plane with two-way movement, up and down. Once the time runs out, we'll switch the controls back to the original one-way input. We'll also need a visual indicator, like a fuel bar, to show that the player has fuel. This way, the player will know when the special controls are active and can watch as the fuel runs out, giving them a heads up before the input system switches back. Alright, let's set up the UI for our fuel system. First, we'll use a progress bar to visually track how much fuel the player has left. For a nice clear look, let's set the background color to dark gray and the foreground color to green. That way, it really stands out. Next, we'll add texture rect nodes to show images that indicates when the special input system is active. I'm not going to stray too far from the Kenny asset pack, so I will use these 2 tap arrows and rotate them up and down to let the players know that they have two-way control. And that's it for the visual feedback. Now that we've set up the visuals, let's handle the input for the new controls using the up and down arrow keys. Instead of sticking with the current UI accept input, we'll switch things up. We'll map the up movement to both the up and W keys so that the players have flexibility. We'll add down movement with the down arrow and S key. And finally, let's make it easy for the players to start and restart the game using the enter key. This way, there's no need for a mouse. You can control everything with the keyboard. This setup should feel smooth and intuitive. The easiest way to handle the fuel pickup is to create another hill template and place the fuel pickup inside it. This will be similar to how we added an extra point pickup earlier, but this time we'll use it to set a has fuel boolean to true. That way we can track when the player has fuel. Once the template is ready, we'll preload it into the array of hill templates so it can spawn in randomly during the game. First, we declare some variables to keep track of things. Has fuel is a simple true or false boolean to check if the plane currently has fuel or not. Plane speed is how fast the plane can move when the fuel-based input is active. Fuel time tells us how long the fuel will last after picking it up. Current fuel tracks the remaining fuel in real time, and fuel bar is a reference to the progress bar so we can show how much fuel is left. In the physics process function, where the movement logic happens, we check if the player doesn't have fuel. If not has fuel, and only under this condition will the plane behave normally under gravity as before. In the on-plane area entered function, we check if the plane collided with an object named fuel, and we set the has fuel to true because the player just picked up the fuel. This tells the game to switch to the new controls. We make the fuel bar visible on screen so that the player knows the fuel is active. Then we set the maximum value of the fuel bar to how long the fuel lasts, the fuel time. This scales the bar correctly. Next, we fill the bar by setting the current fuel to the fuel time. Then we call area.queueFree to remove it from the scene. And now it's time to start counting down. We use await getTree.createTimer and pass in the fuel time .timeout. This creates a timer for exactly how long the fuel will last. The await keyword pauses the function until the timer finishes. When the timeout is called, the game knows the fuel is gone, and the has fuel boolean can be set to false. We will handle this updating the progress bar and the new input in the process function. I could handle the input in the input event function, but I wanted to show how I would handle input in the process function, as mentioned previously. The process function runs every frame, so first we check if has fuel and not is game over is true, because we only want to apply special movement and fuel logic if the plane has fuel and the game isn't over. If the player is out of fuel or the game has ended, we skip everything else inside this block. Here we're burning fuel every frame. The delta is the time since the last frame, ensuring smooth, frame rate independent fuel reduction. Using max makes sure the current fuel never goes negative. Then update the fuel bar by setting fuelbar.value equal current fuel. This updates the fuel bar so the player can see how much fuel is left. If the fuel is completely gone, we set has fuel equal to false, so that the game switches back to the gravity-based movement, and hide the fuel bar since there's no fuel left to show. To handle movement, if the player presses the up key, the plane moves up by decreasing its Y position, using plane speed and delta for smooth, consistent movement. Similarly, pressing the down key increases the plane's Y position, moving it downwards. This code lets the player control the plane in two directions when there's fuel. It also handles fuel depletion, updates the UI, and reverts to the normal mechanics once the fuel runs out, providing smooth gameplay and visual feedback. And that's a wrap. We haven't just created another Flappy Bird clone. Instead, I hope that along the way you've learned something new or discovered a different way to approach tackling some familiar game mechanics, all in 137 lines of code. And with that, we've come to the end of another video. If you want to play the game or check out the project files, it's on my itch page. I will leave a link to it in the description. It's totally free and I think that is a great place to start. Thanks for watching. We've discussed a lot today. Core mechanics with no gimmicks. I do hope this video was helpful. If you liked the video, give it a like, and as always, subscribe and turn on notifications so you'll know when I upload another video. And speaking of my other videos, why not check out another one of my videos right here. This has been Dirago Games.